Let's apply what we learned about pump efficiency to a different scenario. In this problem, we have a biodiesel fuel pump with a 15/16 inch diameter nozzle, and it's used to fill an environmentally friendly bus. If it takes 7 minutes to fill a tank that holds 120 kilograms of biodiesel, what is the velocity at the fuel pump nozzle exit? And we're also given a note that the density of biodiesel is 880 kilograms per meter cubed. So in this problem, instead of using water, which we had a known density of 1,000 kilograms per meter cubed, we're now moving biodiesel. To start this problem, let's identify what we're trying to find. We're trying to find the velocity at the fuel pump nozzle exit. When we're thinking about pump efficiency, you might immediately jump to the efficiency equation, which is shown here on the screen. This equation does have the term velocity in it. However, the information that's provided to us in this problem does not have the different components in order for us to utilize this efficiency equation. We're not given voltage, we're not given current, nor are we given any information about efficiency. So this is not the equation that we need to use. But you were also given another equation that involved velocity, and that was velocity equals volume over area times time. This equation, we have components from our problem statement that we can utilize in order to find velocity. Although we're not given volume, we are given mass and we are given density, and we know that those quantities are related to one another. So I'm feeling confident that we can potentially find volume. In order to find area, we would need to have the diameter of the nozzle, which we are given as 15/16 of an inch. Additionally, we're given the time that it takes to fill the tank and the mass that the tank holds, along with the density of the biodiesel. So let's write down our known information. We know that we have diameter, which is 15/16 of an inch. We also know that we have time, which is 7 minutes. Additionally, we are given the mass, which is 120 kilograms. And the final piece of information that we were given is the density of biodiesel, which is 880 kilograms per meter cubed. Before we can start plugging these values into our formula, we need to make sure they're in the form of the units that we need. Diameter is in 15/16 of an inch, which is not metric units. We want them to all be in metric units, so you want to convert that diameter into meters. We know that there's 2.54 centimeters in 1 inch, and there's 100 centimeters in 1 meter. This gives us a diameter of 0.0238125 meters. Moving to time, we see that it's written in minutes. However, we want time to be in seconds. We know that there's 60 seconds in a minute, which gives us 420 seconds. Our mass is 120 kilograms, and our biodiesel is 880 kilograms per meter cubed. Both of those are in metric units and in the form that we want them to be in. So we won't have to do any unit conversions for that. Now let's start looking at our velocity equation. Our velocity equation is volume over area times time. The big red flag with this formula is volume. We're not given any specific volume for our situation. However, we are given mass and we are also given density. If you recall in the previous presentation when we introduced the concept of pump efficiency, we said that mass is equal to volume times density. So we can rearrange for volume to see that mass divided by density is equal to volume. So here, where we have volume in our equation, we can replace it with mass divided by density. So I'll rewrite our velocity equation to say mass divided by density times area times time will give me velocity. Now these are all terms that I have. I have mass, I have density, I can calculate area because I have diameter, and I also have time. So let's put in our known information. Our mass is 120 kilograms. Our density, which was given to us as 880 kilograms per meter cubed. Remember, we're not working with water, so we have to change it to the density of biodiesel. Then for our area, we're going to use the equation pi over 4 diameter squared. Our diameter is 0.0238125 meters. That term is squared, and then we're going to multiply that by our time, which is 420 seconds. After calculating it out, we get 0.729 meters per second. So although we didn't use the efficiency equation, we still use some of the principles that we talked about when we introduced the efficiency concept. We utilize this velocity formula in order to find the velocity that the fuel is moving at the exit. We also had to utilize the relationship between mass, volume, and density in order to substitute in mass and density for volume. One last thing, even though the problem did not ask for it, I think it would be a good opportunity here to calculate flow rate. So let's calculate flow rate here. Remember, flow rate is a volume over time, but it can also be calculated by doing velocity times area. Both of these terms here, volume over time and velocity times area, will yield the same units of meters cubed per second, or volume over time. So our velocity is 0.729 meters per second. Our area we can calculate as pi over 4, diameter 0.0238125 meters squared, and then we can find that to be 0.0003247 meters cubed per second. And you might be thinking, why would she want me to find flow rate when it looks so weird like that? And that's because we're not going to leave it in terms of meters cubed per second. We're going to put it in terms of liters per minute. Remember, when we do flow rate, which is represented by the capital Q, we typically want to present it in liters per minute. This is that term that we would present to people to help them better understand what's happening with the fluid moving from our pump. So I'm going to convert this into liters per minute. I know that there's 0.01 meters cubed in 1 liter, and I also know that there's 60 seconds in 1 minute. When I calculate that out, I get 19.48 liters per minute, which is a lot easier to understand and visualize how fast that water is moving. We have a velocity of 0.729 meters per second. If we were to have to calculate efficiency, we can take that velocity term and plug it into our equation. However, to visualize 0.729 meters per second, that's a little bit more difficult to see. And so maybe we would want to present it to people as our flow rate in terms of volume per time and say that there's 19.48 liters per minute, and say that the fuel is pumping at a flow rate of 19.48 liters per minute.